Okay, hi, my name is Yun. I'm a graduate student in BBE, and my midterm presentation topic is computer generated holography. I'm actually going to spend the first half of the presentation talking about holography, but hopefully that'll get us to better understand how computer generated holography works. So, what is holography? Holography is discovered by Dennis Gaber, who won the Nobel Prize in 1971. It is a technique that allows a wavefront to be recorded in the form of an interference pattern. This recorded hologram can then be used to reproduce the light field that represents the recorded 3D scene or object. So, for example, if you have a tree nut that you want to take a holographic photo of, you place it in front of the film. You use the holography method to record the light field that's bouncing off this tree nut. And when you later remove the object, you can still see this object as if it's still present in front of the film. So we can start by comparing a normal photograph to holograms. Let's say you walk down the street and you saw a tree that you want to take a photo of. And we can use the example of the simplest form of camera, which is a pinhole camera. If you place this dark room or box with the pinhole in front of the tree, after some time of exposure, you can get a photograph of this tree. And this is only capturing the view from a single angle. So only the light waves that are geometrically able to enter the pinhole can be exposed onto the film. So in order to capture the tree from different angles, you might think that, okay, maybe I need to get rid of the pinhole so that the light from different angles can be um, can be reaching the film. But the problem is that you will probably just get a blur because now the film is overlapped with light waves coming from all different directions and they're indistinguishable. So to enable to discriminate the light waves coming from different locations, we need to account for a second component of the light wave. So other than only recording the amplitudes, in normal photography, instead in holography, we are able to account for the phase of the light waves. So let's say you set up a scene. This is a picture I got from the YouTube video that I learned holography from. So let's say you set up a prop on your table and you shine a light on it. Now this prop or scene um, creates a very complicated light field that will enter your eye. And our goal is to capture and recreate the full state of this complex light field, including all the distortions or reflections that are caused by any optical or material surface properties that you have from this prop. So in practice, how are you gonna generate a hologram from this scene you've set up on the table? So first of all, you will need a single frequency laser in order to have a coherent wavefront. And once you turn on the laser, you want to first split the laser up into two different optic routes. The first route creates a reference beam that directly reaches the film. The film is here on the bottom. And the second beam will hit the object first and then reaches the film. So the object wave is the wave that you record the light field of your object with. So now on top of the object light field, what you have additionally compared to normal photography is that you have a reference wave that's coming into the film in the same time. So this is how holography allows you to record not only the intensity, but also accounting for the amplitude. Meaning that when these two light waves hits the film, if they are in phase, then you get a really bright spot. If they're out of phase, then you get a weaker or darker, dimmer spot. So now everything you're recording has taken account your phase due to the reference wave you're using. So this is another YouTube video that I wanted to show you. So if you're taking taking single shots of this prop, this is what you're gonna get. You're gonna get your normal photograph of one point of view. And instead in holography on the right-hand side, you can see that there's many different point of views. And you can really even see, for example, the distortion of that little pie creature behind your beaker. So now let's get back to the more theory side of things. How are traditional holograms generated? So in Gaber's Nobel lecture, he proposes the idea of adding a coherent background, which is a reference wave. So the concept is, what if on top of the object wave, we mix it with another wave whose phase we know? So if let's say your object gets placed on the point B and you have a reference wave coming from point A. So now anything that hits this photographic plate, which is your film, depends on both the reference light field and the object light field. So the intensity you're recording really is just the square of the absolute value of the total light field. And if you expand this term, the first two terms are just the intensities of your reference light wave and your object light wave. But the really important part is this third term, which you can see that it depends on the phase difference between your reference and object wave. So this is recording the interference pattern on the film. And it's recorded as microscopic fringes on the film. So when you reshine the reference wave on this bottom graph, which is the reconstruction step, now these tiny fringes acts like diffraction gratings, like the double slit experiments. And this diffraction of the reference wave will recreate the original wavefront from your object. And the recorded holograms on the films often look like random fringe patterns. And this is because this is a superposition of the spatial frequencies. So you can view it as a 2D Fourier map that encodes a 3D light field. So last thing about the traditional holograms is I wanted to talk about the math. I think it really helped me understand how holograms are generated. So if you define the reference wave and object wave hitting the film as R and O, you can write it as a amplitude term, which is absolute R times the complex number to describe the wave behavior with its frequency and phase. So the total field that hits the film is R plus O. And since the film always only records the accumulation of the field that's hitting the film, you only see the intensity. And again, the intensity is equivalent to the absolute value of the total field and square. And if you expand this term again, you will be able to get 4 different terms. And the star is just the complex conjugate of the complex number R. So for example, this first term, R star equals to the square of the absolute number of R. So this is just the amplitude of R square, which is the intensity of the reference beam. So the first term is just the background illumination from the reference beam. And the second term, again, is the intensity of the object wave. So if you only have this term, this will be a normal photograph recording the wavefront from your object. The really interesting part is the complex terms that are left here, the third and fourth term. So RO star is the reference wave times the conjugate of the object wave. And if you expand this term, you can see that the intensity of this term is only dependent on the phase difference between your reference wave and the object wave. So meaning that R and O is interfering, and it creates a bright fringe when they're in phase and it creates a weak fringe when they're out of phase. And the last term, this is just a mirrored version of this third term, the R star O. So this is a complex conjugate of R O star, and physically it also creates a mirrored image, and it's usually considered as an artifact when you're creating holograms in real life. And there are ways to get rid of it or weaken it by, I think, pointing your reference light in different angles, but I'm not gonna get into it. But basically, you can see if you look at the math, you can tell that everything that shows on the film really depends on the interference pattern, which is the phase difference between your reference and object wave. Okay, so now we can finally get into computer-generated holography. So now that we know how a holography is generated, a computer-generated holography is a technique that uses computer algorithms to generate the holograms without placing a real project. So you use your computer to simulate the interference pattern that generates a desired virtual object or pattern. And this generated hologram, you can either print it onto a film like a traditional hologram, or it can be digitally displayed by a spatial light modulator. I'm going to explain what a spatial light modulator is in a second. And this is just a overview of computer-generated holograms. And unfortunately, I'm not a computer science person, so I won't be able to get into the technical methods of these different strategies, but I just wanted to stress that this is still an ongoing challenge because, as you can guess, to compute and simulate the hologram pattern in a very fast and high quality way is pretty computational challenging. And with deep learning and everything, I think there's new methods to compute these holograms every day. So I just wanted to stress that this is a ongoing topic. People are still working on it. Okay, so I wanted to talk about computer-generated hologram in a more specific example, which is using it in an optical system. It's also called a Fourier computer-generated holography. So let's say you want to put you want to generate a hologram in your microscope for whatever reason that I'm gonna explain in the end. And usually in a microscope you have a laser beam, which creates a coherent light source. So when the wavefront comes into the displayer, which is the SLM, so a SLM, the spatial light modulator, it's a modulator that can shape your wavefront based on different phase pattern that you program into it. So it's basically made of liquid crystals in the modulator device. And if you input a certain program, it applies different voltage to these little mirrors for it to shape the incoming wavefront into a desired phase pattern. So now that your coherent wavefront enters it can be shaped into a specific phase pattern going forwards. And it will continue to propagate into your optical system. So usually it includes a lens. And what the lens does is that it performs a physical Fourier transform and then encode this interference pattern into a 3D illumination pattern. So the task, so the whole process is that you want to first know what pattern you want to create, and then you want to input all the optical lens and components and all these different focal distance that's in your optical system into your computer, and your computer will be able to compute the interference pattern that you can then display on your SLM. So then the next question is, how do we retrieve this phase pattern that you can show on your SLM in order to generate this desired pattern? So there are many methods, as I mentioned earlier, but one of the most popular and simplest method is doing it by a iterative progress using the Gertzberg-Saxon algorithm. So to initialize the algorithm, you want to first input the amplitude and the phase of your light source. So usually the amplitude is just whatever intensity your laser is, and you can input a random parameter for your phase. And once it enters your system, you will have a estimated light field at plane A, which is where you put your hologram film or your SLM like display. And then your light will continue to propagate down your microscope through, for example, different lens. And again, this is performing a Fourier transform. When it reaches your plane B, which is the target plane where you want to show your 3D pattern, it's going to have an estimate of what this light field looks like. But during the initial iterations, it's probably not going to look very good because you randomize it with a phase that you don't know of. So what you need to do here at plane B is that you want to slightly modify the amplitude to match the observed data better so that you get a slightly more realistic light field that matches your desired pattern at location B. And then you reverse propagate this light field back to plane A through a reverse Fourier transform. And then you can have a re-estimate of your light field at plane A, but then now the amplitude probably looks different than your initial amplitude profile of the laser, which is what you know. So then again, you will modify the amplitude to match the laser profile slightly better, and you'll have a renewed version of a estimated light field. So you continue this process for several loops, and the goal is then to ultimately retrieve a phase map that reconstructs the target light field that represent your desired pattern, like the 3 little dots that I showed here. So now that you have this phase map, you can go back to show it on your SLM and to illuminate this 3-dot pattern on your desired space. So why is this important? Like, how is this useful other than showing cool 3D pictures? So the reason why I chose this topic is because I study neuroscience, and if we combine the two photon microscopy stuff we mentioned in class last week, we can use computer-generated holography to do 3D neural stimulation. And so as we mentioned with two photon microscopy, you can confine your focal point at a very confined area in the brain, and you can penetrate the brain till around like several hundred microns. So using two photon combined with the holography method, you can then create these little light blobs in their brain in across different Z positions, and they are fairly confined, meaning that um, you can then simulate at you can then shine this light blob in a very specific spatial location. So what this does is that um, this is a real imaging example from a previous lab that I've worked at. So whenever you see a green arrow that shows up in this video, it means that it's performing holography simulation in that spot, and the red pattern is imaging the neural activity using GCamp. It's a sensor used to record neural activity. So you can see using computer-generated holography, you're able to stimulate the neurons in different planes in the brain, and you can stimulate several neurons in the same time. And why is this useful? So another study from the same lab, they were studying the encoding of visual stimulus using mice. So for example, if you show a mice different grating, like moving gratings, you can observe a certain fluorescent signal which represents the neural activity of a certain neuron. So for example, if you look at these like green patterns, you can see that this neuron that we're seeing probably reacts most to a horizontal grating instead of a vertical grating. So what they did in this study is that they first observed what the neuron is responding to when they show when they showed the mice different visual patterns, and then they try to use holographic stimulation to then recreate this visual activity they're seeing. So on the second row, what you're seeing is that they turned off the visual display and use holographic stimulation to recreate a similar neural response from these neurons. So what this really all means is that we now have the technique to not only read by microscopy imaging techniques, but also write spatial temporal neural signals inside the live brain. And I think that's really cool. But I'm also a neuroscience nerd, so you tell me if it's cool or not. Okay, that's it. Thank you. Have a good midterm break, everyone. Bye.